Okay, welcome back. We're now going to look at the underdamped case in detail and the imaginary solutions that come out. But just real quickly, watch what's happening. This is an underdamped case. It looks a lot like what happens in the undamped case, except that we have a decaying amplitude. All right, so the amplitude gets smaller on every oscillation. It's decaying away in it looks like almost an exponential kind of way. So we somehow need to get that to come out of our solution. And right now, our solution does not look like it's sinusoidal at all. So we need to figure out how to make it sinusoidal. So let's switch back to the iPad screen. Okay, so we should see the screen coming up. Okay, and so this is where we had left off in the previous video. We had the differential equation for damped oscillations, the new term being the bx term, the bx dot term, because that's velocity. And then we had derived this solution for it in the general solution with the C1s and the C2 term. And we had defined R to be negative E plus or minus the square root of B squared minus 4mk all over 2m. So we know that things will get a little bit crazy when the radical is negative, okay? So we get complex answers when the radical becomes imaginary, and the radical is imaginary when B squared is less than 4mk. Okay, so when the damping is too low, this is going to become imaginary. And somehow that's going to lead to sinusoidal oscillations. So that's what we want to explore in this video. Well, to do this, though, it helps because once we start talking about oscillations, we'll want to talk about angular velocities. And we had a decaying oscillation. So we want to talk about a decay constant. So we're going to rearrange this R into negative B over 2m plus or minus. And then we're going to put the square root over the whole thing. And when you put 2m into the square root, it becomes 4m squared. You have to square the factors when you bring them into a square root. Usually in algebra class, you bring them out of the square roots when they are perfect squares, but we're going to do the opposite because we're going to see some nice things happen. Okay, so the first nice thing that happens is that b squared over 4m squared is just b over 2m, which we see in front of the radical, being squared. Okay, so we have b over 2m showing up in more than one place. So that might be an interesting set of parameters. All right, and you can see that the second term in the radical simplifies pretty nicely down to k over m. Okay, now k over m is an old friend. That was omega squared. In fact, we just did our whole lab on omega squared equaling k over m. Now, the problem is we're going to have a different omega in this solution because when we have damping, we're going to get some sort of oscillation when we're underdamped, and there will be an omega, but it is not k over m. This we'll call omega naught, which is, we'll label that the damping with no, I'm sorry, the angular velocity with no damping. With no damping. Okay, we'll have to have a slightly altered angular velocity because damping will slow things down. They'll create a little drag in the oscillations, so they will slow things down. All right, so that's one thing that we have in there. Okay, and b over 2m showed up twice. So we're going to give it a new name called gamma. It's a Greek letter gamma. Okay, and that will be b over 2m, right? So it is the Greek gamma. And that is the decay constant. We'll see why it's the decay constant as we work through the math. All right. And then we will be able to define one more thing in a moment, okay, which is the angular velocity for our system, which will be the square root of omega naught squared minus gamma squared. Okay, so this is going to be the angular velocity for damped oscillation. Or I could say with damping. So it's related to what the angular velocity would have been if there was no damping. If there's light damping, gamma will be very small and we'll get almost the same thing as we would have gotten without damping. But as the damping gets heavier, there'll be a bigger difference. Okay. Now let's see, let's keep going with this. Okay, so we can rewrite R now. R can be rewritten as negative gamma plus or minus the square root of gamma squared minus omega naught squared. Clean that up. Okay, so extend that a little bit. Okay, so I literally just took this and I used the new definitions. Okay, now we can see gamma squared minus omega naught squared is exactly the opposite of what we would have expected for omega. Okay, so omega squared would be the opposite of that. So what we can do is say this is negative gamma plus or minus the square root of the negative of omega naught squared minus gamma squared. Okay, and that gives me that R is negative gamma plus or minus the square root of negative omega squared. Okay. Now, you may remember that when you have the square root of a negative, it gives us I, the imaginary root. Okay. So R is now complex. We get plus or minus I, and since it's omega squared in a square root, we can bring out the omega. So this is complex because this part is real and this part is imaginary. All right, so this is how we'll define R as we move on. Okay, so this gives us an R1 of negative gamma plus I omega, and an R2 of negative gamma plus sign minus I omega. Okay, the solution we have is the same as before. Okay, so it's going to be C1 e to the R1t plus C2 e to the R2t. Now, we're going to end up having complex coefficients here. I'm going to do a couple of things in the next step. First of all, I'm going to change my C1 to an A1. All right. We'll see in the end, I want to get back to having a C1 and a C2. I'm going to just rename my constant A1. Since it's not defined yet, we can call it whatever we want. And I'll do the same thing for C2 and make that A2. All right. And then I'm going to write in that this is E to the negative gamma plus I omega t plus, and then it'll be A2 e to the negative gamma minus I omega t. Okay, so what happens here? Well, let's just do some algebra. Hopefully, let me write this out on the side. You remember that e to the a plus b is the same as e to the a times e to the b. Usually in algebra class, we go the other way, where you add up the exponents. But if you have a sum of exponents, you can distribute them. You can make them into multiple factors, okay? So we can rewrite this as x equals a1 E, we're going to distribute the t, by the way, to both terms here and here at the same time. Okay, so we'll have e to the negative gamma t. Oh, that looks like exponential decay right there in that factor. Times e to the I omega t. And we don't have any idea what that's doing yet. Plus a2 e to the negative gamma t times e to the negative I omega t. Right? Let me get this out of the way for now. Okay, so that's what our solution is looking like so far. Okay, now a nice thing is we have common factors. So let's bring those out. It turns out we have the same decay factor, which is why we called gamma the decay constant for both terms. Plus a2 e to the negative I omega t. Okay, and that's our solution. It's just not in a very helpful form because we have imaginary exponents on e. All right, so we're going to perform some magic using Euler's equation, which will be in the next video. Okay, and we're going to just say that this is equal to e to the negative gamma t times c1 cosine omega t plus c2 sine omega t. Now, if you look at this, okay, you have no idea where that came from yet. That'll be in the next video. But when we look at this, okay, it fits all of the ingredients, okay, of what we're looking for, all right? We have decay. This is exponential decay right here. And this is the old oscillating solution. The only difference is that omega is a little different because we have a damping part of it. So it's not just square root of k over m. Okay, I'll say with omega squared equaling the old omega minus gamma squared. Okay, so it's going to go a little bit more slowly than it did before in its oscillations, but it's going to oscillate before, which is exactly what we saw in MATLAB. Okay, the next video is going to make this big step. Okay, using Euler's equation to get us from a1 e to the I omega t plus a2 e to the negative I omega t to the old solution that we had. Okay, so that will be coming up shortly.